Welcome back. So now we are in the next part on the relational algebra, which is again a theoretical part. I will first start with a question on domains, clicker question, and then we'll continue with the course. So let me switch over. This is the question. Which tuple satisfies the constraints implied by this schema? Create table my table, HR3, B numeric 5, C dates, D Boolean. These are 4 tuples. And you need to find out the one of them, there's one of them that satisfies the constraints. Note that when I say satisfies the constraints, I mean it is in the relational database, because it might be that some of them you could insert, but then they would be modified to fit, right? Here, I really ask what should really be in the database satisfying the constraints. Okay. Interesting. We have a majority. Is the majority correct? Something is changing. Let me give you more time. Okay, let me tell you the majority is incorrect here. But you have one chance to change your answer. Few more seconds. Yes, yes, yes. Continue, continue, continue. Yes. Okay. You're awesome. This is the correct answer. Okay, there was a small trap here because I swapped C and D. Oh, I cannot show it here, sorry. I swapped C and D, but it doesn't matter. There is no order, right? It's the same map. So this is why it's fine. So you see ABC is a char 3, it's 3 letters. 1, 3, 2, 4 is a numeric of 5 because it has only 4, so that fits in 5 too, and 0 after the decimal period. D can be null because there is not null in there, so it's not forbidden. And the last one is a date, so this is fine too. The first one, what's wrong? Yes? Exactly, A is wrong because there are 4 letters, exactly, so this is wrong. Why is the second one wrong? Maybe the microphone could be useful. Why is the second one wrong?
The pointer of the bool is E, not
E.
D.
Yes, exactly. So E would be outside of the schema. There is no colon E. So indeed, and the third one, why is this wrong? Technically, you could insert that, right? But then it would be changed.
Because it's not defined that numeric 5 is taken as 5, 0 kind of. So
Exactly.
There's no decimal places allowed.
Exactly. You cannot have any decimal places because by default, that's 5, 0. So 1, 3, 2, 4, it would be changed to 1, 3, 2, 4.0, basically. The 5 would go away. Yeah, perfect. So this is it. So this is the final one. Let me go back to the slides. Relational algebra. We have 10 minutes until the break. All right. So where are we? We defined a formal model for a relational database, which is plenty of relational tables, where we saw that we have attributes and we have domains for these attributes, for domain integrity. And we have what's called the extension of the relational table, which is the actual data, a set of maps. We saw that the maps could also be called tuples. If you use the other definition, they could be called records. I'm going to try to stick to the terminology records to be orthogonal to the mathematical definition today, right? So I just say that the table is a set of records, but of course the records are maps. Okay. So we know how to define relational tables. The definition that I prefer for that course is that it's a set of maps that have identical support. The alternate definition would be that it's a set of tuples in the sense that it's a relation over domains. And as you know, a mathematical relation is a subset of the Cartesian product, so it's made of tuples. So we know how to define relational tables, sets of maps. Now, what's next is that we'll see how to manipulate relational tables. Not just create them and populate them, we'll actually do calculus with relational tables. So what this is called is data manipulation language. What we've seen so far is data definition language. So it means you create a schema, you specify the attributes, you specify the domains, you specify unique, not null, the default value, the constraints, the primary key, foreign keys, and so on. But this is all data definition language. Now we'll go into data manipulation language. The name for that is relational algebra as opposed to the relational model that we've seen 2 weeks ago. And relational algebra sounds very fancy, but it is actually fancy. It's really not very different, as we will see from, in mathematics when you do calculus and you have algebras. So you probably know these things. Who is a mathematician here? Do we have mathematicians? No mathematicians? On Zoom, do we have mathematicians?
Raise your hand if you're a mathematician.
Is there a mathematician in the room? Okay, no mathematicians. Okay, but that's okay.
Oh, we do.
Oh, there is?
Department of Mathematics.
Okay, Department of Mathematics, wonderful. Okay. So you know all addition, multiplication, and so on, right? This is taught in primary school. Back in the times, there was somebody called Évariste Galois, who was young. He was like 18, 19. And he was brilliant. And what he did is he took addition, multiplication, and so on, but he abstracted it away. He basically said, okay, addition is just something that works with numbers, but you could forget that these are numbers. You could just say there is a set of things, and then we take a thing plus another thing and get a third thing. So this was an abstraction from addition. And then he started looking into the properties of the operation, so plus, for example. So, for example, he could notice that under some condition, A plus B is the same as B plus A, which is called, what is it called? A plus B is the same as B plus A? Commutativity, exactly. And what is the other one? A plus B plus C is the same as A plus B plus C. I hear it? Yes, associativity, exactly. Associativity. So commutativity, associativity, then you have the property that something plus 0 equals that same something. That's called a neutral element. You have the property that something times 0 is 0. That's an absorbing element and so on. So you can actually come up with plenty of properties like that. Back then, nobody took him seriously. Nobody took him seriously. They were considering he was just playing with a game and what he's doing is just a toy. As it turns out, he just invented the notion of groups and all the subsequent concepts like rings, fields, vector spaces that came later with the linear algebra and so on and so on. And in fact, he had just revolutionized the whole field of mathematics and created a whole new domain. And in fact, one of the consequences, it's actually absolutely wonderful, is that you know the complex number I, right? I squared is -1, right? The way it used to be done before is that that's why it's called imaginary. It's like, imagine that there is a number I that when it's squared, it's equal to -1, and people were just doing the math and it was magically working, but nobody really knew why, because this I came out of nowhere. It turns out that thanks to this theory, you can define I mathematically with all kinds of tools. It's actually the quotient set of the set of polynomials divided by s squared plus 1, and you take the equivalence class of x. So I don't know if that actually makes any sense, but what you should understand is that one of the consequences of this work is the formalization of the set of complex numbers. But anyway, now coming back to the lecture, what we learned from that is that these sort of things that you do with addition and multiplication, it doesn't only work on numbers, it works on anything. And because it works on anything, in that case, it's matrices. By the way, matrices are powerful enough to represent any groups. That's called representation theory. But today, this is what we will do. And I think this is super cool. We actually are going to take tables, and we are going to use these operators and manipulate tables, and taking two tables, creating a third tables. That's what we are doing. This is why it's called relational algebra. Think of it as a big calculator, but instead of numbers, it's relational tables that we manipulate, right? Does it make sense? Okay, this is the high level, but of course, I have yet to show you what we are going to do with the tables. Let me check the time. Okay, so we'll have also unary operators that take one table and return the table. We'll have binary operators, that's like plus and multiplication. And the high-level summary, it's again one of these restaurant menus that I told you about, right? I did the same with the type system, with all the domains like integer, strings, and so on, dates. Well, it's the same thing with the relational algebra. We will work on sets. We will also filter tables. We will rename tables, and we will join tables. And this is the question that you asked before regarding the foreign keys, right? So this is the menu. So you see, it's not just addition and multiplication. It's a whole bunch of operators that we can actually make work on tables, right? So as a reminder, before we take the break, a relation has attributes and domains associated with the attributes and an extension. We add a little something today. We'll also give a name to the actual relation. That shouldn't really surprise you, because in PostgreSQL, we give names to the tables, right? When we created a table, we give it a name. So I do the same thing today. I'll add this extra line on top saying this is the relational table R, and it has columns A, B, and C, right? So it's called a rel var, but you don't need to be too scared by that. It's just a relation that has a name or knows its name. Okay. Let's stop here. Let me let you go to a break. And in the next hour, we'll just explore this beautiful relational algebra and do calculations with relational tables. All right. So I'll see you in 15 minutes. So 15 past 11. Thank you.